Okay, surface integrals. Well, actually, you guys are already familiar with surface integrals. You learned this back in calculus too when you were asked to find the surface area of revolution. Remember, it was a nightmare, that problem, because I mean, not evaluating the integral itself, just the setup. Because if you were given functions of x, if you wanted to rotate about the y-axis or the x-axis, well, it was always tricky to see how we were going to set up the integral as a function of x, as a function of y. So that's what made it a nightmare. Well, so and in the same way, we have derived this integral, because I will derive this integral. Well, how did we go about the surface integral? Well, again, area under the curve, infinitely many rectangles, right? Find the area of those rectangles, add them up together. Well, but for a surface of revolution, what do we have? For the simplest case, we would have the following. We would have this line, that's like the smallest possible or the simplest possible setting. And what would we do? Rotate it and create what we call the frustum of a cone. All right, so um, like this. That would create a solid revolution. And what would we be calculating? The surface area, which you can think of the amount of skin of the body, if you will. All right. So, well, how are we going to take or calculate surface area of other solids? Because we're no longer going to do solids of revolution. Well, that's good. Actually, despite this looks more complicated, to some extent it will be a lot easier to set up. And well, since at this point you guys are masters in integration, you should not have any problem with the integrals we're going to set up. All right. Okay. So because think about it, for instance, most of the surfaces in space, they're not symmetric to any of the axes, unless you are talking about maybe a sphere, for instance, right? For a sphere, you can easily go back to the calculus 2 techniques, all right, or calculus 1, or I don't know. What else? Maybe the area of an ellipsoid, the surface area of an ellipsoid. You can go back to the techniques from Calc 1, Calc 2. But in this case, think about all of the surfaces we have discussed in this course. Well, not all of them are symmetric. So the revolution thing, it's no longer in the conversation. So these 2 pi right here, in front of the integral, that's to describe well, that came from the rotation, from finding the area of a circle and adding infinitely many of those, right? So, okay. All right, so how are we going to do it? Look at this surface. This surface is definitely not symmetric about the x-axis, about the y-axis, or about the z-axis. So we need another way to describe this. Okay, what do we need to derive this integral? Well, we need, number one, the area of the parallelogram formed by 2 vectors. So let's revisit section 13.4 for our purpose. And number 2, the equation of the tangent plane to a surface. That's 15.6. We're going to put those 2 ideas together. Because again, so consider this surface right here, all right? So again, we want to find the amount of skin, if you will. So, but how are we going to partition this surface? Well, we're no longer partitioning into rectangular prisms, right, or rectangular boxes, because that's a volume. So for surface area, I'm going to, we will partition this into. Did you see all these little squares? Those are planes. So the more you zoom in to this picture, if you think about it, the more you zoom in, the flatter it will look. Well, what is that flat surface? Isn't that more like a plane? So what are we going to do? We're going to find the area of a plane and add infinitely many of those areas of the plane. All right, so that's how we're going to get this. Okay, but first of all, we need a couple of vectors. We need to deal with some differentials. Well, number one, How do we find the area of the parallelogram formed by the vectors u and v? Do you remember that one? Area equals, what is that? The magnitude of
u cross v.
Yes, the magnitude of u cross v. Correct. Thank you. The equation of a tangent plane to a surface, pretty easy. Even though we go like ax plus by plus cz equals to d, I'm going to solve this equation for z equals to ax plus by equals to c. So I'm writing this equation in explicit form for z. All right? Okay. What else are we going to do? Okay, we need vectors. We need these vectors u and v, right? Okay, so you know what? Let me write down the differential. dz equals to a dx plus b dy. Oh, wait. This is a plus c, not equal c. Well, the derivative of c right here will be 0, right? All right. So, well, because this is differential, this is infinitesimal change, let's go about the finite change. You know that element? I'm going to change these with deltas, first of all. Delta z equals to, what's that? A delta x plus b delta y. All right? Now, I need two vectors here. Okay, so what is this delta x? What is this delta y? So from our partition, okay, let me highlight the partition I'm going to use to derive this integral. So I'm going to take, say, this partition, right? It's a little tiny plane. You guys agree with that? Well, that picture, this bubble here is zooming in. It's zooming in the picture, and well, look at this plane right here. It's actually this plane right here, spanned by these two vectors, v and u, where v involves a delta y and vector u involves a delta x. Are you guys following me here so far? Okay, but also notice these vectors, how they go up, right? So there's also some delta z involved for both of them, right? Okay. All right, so let's define this vector. So let me write down vector u, okay? So vector u, which is a delta x, no, it's delta x sub I in the direction of I plus delta y sub j plus some delta z sub in the direction of k. However, notice vector u, how it only involves components in the direction of x and in the direction of y. Do you guys see this? So, okay, let me show you this. It's only going in the direction of x and in the direction of z. It's not going in the direction of y. All right? So I'm going to represent this vector in component form in a better way. So that means this vector is delta x, 0, delta y. Okay, let me get rid of all this. The second vector, v. Okay, notice how this vector v has components in the direction of y and in the direction of z. You guys following this? Yep.
Why on that last?
Because it's delta z. Yeah, delta z, not delta y. Yeah.
And the y is 0.
It's 0. That's because it's only going in the x direction and the z direction. Notice this vector is not moving in the y direction. But vector v is, let me get rid of this. Vector v, it's going in the direction of y, in this direction, and up in the direction of z. All right? So v, which again in general, that is delta x, I, plus delta y, j, plus delta z, k. Okay? So, but in this case, notice how this time the x component is the one that is 0, isn't it? So this will be delta, 0, first of all. What else? 0, delta y, delta z. All right. So those are the components of these two vectors. Well, what are those two vectors? Those two vectors for which we're gonna get the cross product of and find the magnitude of the resultant vector. The magnitude of that vector is gonna give us what? The area, right? The area of that tiny little plane that adding them up together, all of this will give us the element of surface area. All right. Let's set up our let's rewrite this again. Okay, so we need to write this in terms of differentials. So well, because in this case, think about delta z. Okay, what is delta z? Didn't we write delta z in terms of a delta x plus b delta y? We need this because those are the parts of the equation of a plane. Okay, so I'm going to replace. Okay, I think I need more space in here. Whoops. So I'm going to write delta z. So delta x 0 delta z, but delta z, that is a delta x plus b delta y. All right, but again, what is delta y for the vector in the for vector u whose components are only going in the direction of x and in the direction of z? You guys agree this is 0? Okay, this is 0 because it's not, this vector is not moving in the direction of y. So this will be delta x 0 a delta x. All right. Okay, and in a similar way, I'm going to express this this vector v by replacing delta z in terms of delta x's and delta y. So this will be 0 delta y, whoops, delta z, which again is a delta x plus b delta y. All right. Okay. So again, because vector v is only moving in the direction of y and in the direction of z. That means delta x will be 0. Okay. So that'll give us as a result the vector 0 delta y b delta y. You'll see in a second why I'm writing all these z's or delta z's in terms of delta x's and delta y's. You'll see. So what are we going to do finally? Get the cross product between u and v. That is I, j, k. Okay. That is a vector 0. No, it's delta x 0 a delta x, and the second vector that's 0 delta y b delta y. All right. Well, I'm not going to do the entire cross product here. I'm just going to give you the result, which in this case it's going to be a humongous vector here. It's going to be the following. Okay, negative a delta x delta y, comma b or negative b delta x delta y, comma delta x delta y. So that is the vector. So the magnitude of this vector will give us the element of surface area. That is the area of that tiny little plane that adding them up together, all of them within the region D, that's going to give us the surface area of the area of the surface within those bounds. Right? So let's find the magnitude of this vector. So the area finally will be the magnitude of this cross product that equals the square root of negative a delta x delta y squared plus negative b delta x delta y quantity squared plus delta x delta y all squared. Everything under the radical. All right, so everything squared gives us turns all the negatives into positives. So that is the square root of a squared delta squared x delta squared y plus b squared delta squared x delta squared y plus delta squared x delta squared y. Okay? Did you see this the common factor delta squared x delta squared delta squared y? Let's take out that common factor. So that'll leave us with the following: the square root of a squared plus b squared plus 1 times delta squared x delta squared y. All right? Using product rule for radicals, take the square root of the parentheses, which is just going to be the square root of the parentheses. All right? A squared plus b squared plus 1. What about the square root of delta x squared? Isn't that delta x? What is the square root of delta squared y? Isn't that just delta y? All right? Okay, so we finally got the result we wanted. So, what is that delta x when we add infinitely many of those little skins? Isn't that going to become dx? And same with delta y, that's going to become dy. Okay, but what about those coefficients or those quantities a and b? Where did they come from to begin with? Where are a and b coming from?
Parameterizations of those vectors?
The parameterizations of okay, let me scroll a little up so you can see where a and b come from. Huh? From z, and what is z? What does that represent? The tangent plane, but those are the coefficients of x and y, right? How do we get those coefficients of x and y? Remember, for a tangent plane? We get those coefficients a and b for the equation of the plane. Well, we would need a normal vector, of course. Well, that's chapter 13. No, so I mean, yeah, you're right. You're right. I mean, those are the components of the normal vector. Yes, but for the tangent plane, how do we get those vectors? I mean, those coefficients. Anyone? How do we get those vectors? It's the partial derivatives of the surface, of the equation of the surface that we're finding the tangent plane of, right? So that is the partial of z with respect x, quantity squared, plus the partial of z with respect y, quantity squared. And this is our element of surface. This is the end of the derivation or proof if you want. Now let's have a look at the integral in the next page. Oh, look at that, right? Look at that. Okay, so now this double integral with a 1 in the coefficient represents something else, but you need to be careful because the differential is no longer dA. Looks like it's a D uppercase S because ds is the differential of surface. Wow, what do we mean by differential of surface area? So it's the differential of amount of skin, if you will, right? So, and how do we get that amount of skin? Well, we just derive it, right? Well, my notation here, z versus f, I mean, it's the same because in the end, isn't that the same as saying f of x, y? Right? Well, but this is no longer be a plane. So we use the plane as the simplest surface to derive this idea. But of course, there's infinitely many kinds of surface you can think of. Paraboloids, ellipsoids, you name it. All right. So we're going to use this integral to calculate the upper surface area. We call it the upper surface area because we're no longer revolving the surface about any of the axes. That's no more, all right? In fact, do you see a 2 pi multiplying this integral? In fact, there's no 2 pi multiplying there, all right? Okay, find the surface area of the part of the surface z equals to x squared plus 2y that lies above the triangular region T in the xy plane with vertices the origin to 0 and to 1. All right. So, number one, let's graph this. Let's graph this region first. So. Okay, so graphing this region, we get, so it is the points 0, 0, the point 2, 0, and 2, 1. All right, 2, 1. That's going to give us this triangular region. So the equation of this line, so that is y equals 1/2 x, that is rise 1 unit, run 2 units, right? That's going to give, and the intercept is at the origin, right? So what do we need? So to evaluate the surface, the upper surface area, okay, I'm going to leave some space here for a reason. I'll show you. So big S is the double integral over the region R, all right, of the big S. Tiny lowercase s is for arc length. Don't just so you don't get confused with the different letters. Lowercase s, arc length, uppercase s, surface. Right? Okay, so that'll be the double integral over the region R of the square root. I'm going to change notation to z with respect x quantity squared plus z with respect to y quantity squared plus 1. All right? dA. Well, the dA will become either dy or dx, right? And that depends on how we iterate the double integral as vertically simple or horizontally simple, right? Okay, so what do we need to do? Just find the two partial derivatives of the surface. We're given the equation of a surface, z with respect x, that's 2x, z with respect y, that's 2. Substitute, that's the integral of the square root of 2x quantity squared plus 2 squared plus 1 dA. Okay? So, what are the limits of integration? Oh, I'm actually no longer dA. I'm going to go about dy dx because the region is vertically simple. We already have functions of x. Go in that direction. So it's going to go the lower limit, the horizontal line, 0, the upper limit, 1/2 x, and from 0 to 2 in the x direction. Okay? We can easily evaluate this integral. Let's go for it. So that's the integral from 0 to 2, from 0 to 1/2 x of the square root of, careful, 2x quantity squared. Make sure to square both the coefficient, that is 4, and the variable x, because yes, it is a very common mistake in algebra to forget to square also the coefficient. So make sure to square both, and plus 2 squared, which is 4, plus 1 dy dx. Okay, so that's the integral from 0 to 2 and from 0 to 1/2 x, 1/2 x, square root of 4x squared plus 5 dy dx. Okay, so here we're going to integrate with respect to y. Notice this radical is constant with respect to y, right? So the first integral will be from 0 to 2, square root of 4x squared plus 5 times y from 0 to 1/2 x dx. Okay? All right, so, and again, upper limit minus lower limit, those limits are only evaluated to the y variable because, again, we integrated with respect to y. All All right. So that's going to give us the integral from 0 to 2 square root 4x squared plus 5 times 1/2 x dx. I'm not going to write the minus 0 because I think it's obvious, right? And also, I'm not going to evaluate this integral because, let's have a look at it. What method of integration would we use? U substitution, right? Pretty simple U substitution. Make sure to change the limits accordingly if that's how you want to do, or ignore the limits if you just want to work in the world of U. Then go back to the world of X and use the original limits. That's up to you. But the thing here is when we work with this type of integrals, more often than not, we would get crazy looking radicals. Be sure to simplify these radicals like this. That's the same as saying that the result of this is 21 root of 21 minus 5 root of 5. Think about those problems you did back in Calc 1. No, back in Calculus 2 about arc length and about surface area. More often than not, we got these crazy radicals, right? So, yeah, that's what we're expected to do. All right. Set up, but do not integrate. That's awesome, right? That's awesome. Just a setup problem. A double integral to find the upper surface area for the portion of the plane to x plus 4y plus 3z equals to 24 in the first octant. Oh, that's interesting. So in the first octant, that gives us a lot of the limits of integration for sure. Okay, another way to say the first octant is what? Okay, let me write it down because you may see it one way or another. The first octant means the coordinate planes. That is x equals 0, y equals 0, z equals 0. All right? Okay, so that's what it means by the first octant. X equals 0, y equals 0. Those are going to be somewhere, the lower bound somewhere. All right? Okay. Let's graph the plane, number 1. Let's graph the plane. So the graph of the plane, which looks like... let's speak about the plane to graph it using the intercepts. Okay, make y and z equal to 0. 24 over 2, is that 6? Okay, so that's 6. Make x and z equal to 0. 24 over 4, isn't that? Oh wait, no, this is 12. Whoops. So this is 12. This is 6. And make x and y 24 over 3, that equals to 8. So that's going to give us the plane roughly. All right, let's shape this plane. So that's the surface area we're finding, the area of that little triangle. All right. Okay, so what do we need to do to set up and evaluate this integral? Well, actually, we're not evaluating this integral. That's great. Okay. Of course, we need to know what's going on in the xy plane. Okay, this should work as a review for tomorrow's exam. All we need to know is, one of the most important things here is what's going on in the xy plane. What's going on in the xy plane? Okay, so the xy plane projection. Okay, so do you see this? Okay, x, y, z. X equals 12, y equals to z, y equals to 6. That is this projection, right? And what is the equation of that diagonal line? Well, so it's an equation. It's a line. Y equals to plus 6. That's the y-intercept. And the slope, what is it? 6 over 12 negative. 6 over 12, which reduces to what? A half? Negative 1/2. Negative because it's going down, right? Negative 1/2. X plus 6, right? And we're ready to set up this double integral that calculates the area in green. So I'm shading in yellow for the shadow. I'm shading in green for the area that we want to calculate. Well, to write the integral that calculates the area. Alrighty. Okay, but we need a surface as a function, as an explicit function of z, right? I mean, as an explicit function of x and y for the variable z. Well, we're given the equation of a plane, so how about we solve for z for that equation? So 3z equals to 24 minus 2x minus 2y, and z equals to divide both sides by 3, that's 8, minus 2/3 x minus 2/3, wait, 4, minus 4/3 y. Come on, the partial derivatives of the surfaces are going to be pretty easy to obtain. Z with respect x, that is negative 2/3. Z with respect y, that's negative 4/3. Okay, 3. Let's set up the double integral that calculates the surface area big S, double integral d big S. And again, a double integral containing a ds with a 1 in the integrand represents, what does that represent? Represents surface area. However, if you happen to see an integral or a surface integral with something other than a 1 in the integrand role, that's what we're going to see in a few more minutes, okay? What I'm trying to say is that we put together what we're learning in double and triple integrals. So a double integral with a 1, it's area. A double integral with something other than 1, it's either volume or mass of the planar region, of the planar lamina. Triple integral with a 1, that's volume. Triple integral with something other than 1, that's the mass of the solid, right? Okay, so let's replace ds. Let me make more space for the limits. Okay. Well, actually, I don't need it. So that is the square root of z with respect x squared plus z with respect y squared plus 1 dA. Right? Okay. So that's the integral from 0 to 12. Okay. Do you guys agree with 0 to 12 for x? And from 0, the lower limit, the horizontal line y equals to 0, all the way up to the diagonal line 6 minus x over 2, or negative 1/2 x plus 6. Either way, it's the same. Square root of the partial with respect x squared 2/3 squared plus, or negative 4/3 squared plus 1 dA. Okay, 2/3 squared, that's going to give us what? 4 nines plus 16 nines, that's 25 nines plus 9 nines, 25 minus 25 plus 9, isn't that? Well, wait, no. What did I get in my? Yes, well, I'll just give you the simplified result. 0 to 12. 0 to 6 minus x over 2, that is the square root of 29 over 3 dA. And again, they're not asking us to evaluate this double integral. I mean, we don't need to spend a lot of time evaluating a double integral that it's somewhat simple to evaluate, all right? Yes?
Would it be dy dx and dA?
Oh yeah, dy dx. Here we can iterate at this point, right? dy dx. Yes, because we already have limits, right? Dy dx. All right. Let's have a look at another example. This one we will evaluate it. We'll solve the entire problem. Okay. Find the surface area of the part of the paraboloid z equals to x squared plus y squared that lies under the plane z equals to 9. Okay, I think this is going to be also a good review for the upcoming exam, because what do we have? Two surfaces. What do we do when we have two surfaces? What do we do?
Set them equal to each other?
Set them equal to each other. Why do we set them equal to each other? Because of the dividers. sorry, to find the intersection. But how is that intersection useful to our purpose?
Because it's a parabola, so
Mm-hmm.
intersection working.
Well, yes. Mm-hmm.
So we have.
But I mean, in terms of setting up the double inter or a triple, it doesn't matter.
Because right now it's gonna be from 0 to 9.
Mm. From 0 to 9. Oh no, I mean without the result. I mean, the question is why do we set this up? I mean, do we set these two surfaces equal to each other?
On the roof and floor.
That's one purpose. What else?
Oh, yeah, to find the boundaries.
To find the boundaries, the limits of integration. What else? Okay. In the meantime, I will try my best to plot this surface. Okay, so this is a circular paraboloid which looks a lot like this, and then this is intersecting with the plane, with this plane z equals to 9. All right. Okay, so why do we want to do that? Yeah, to find the boundaries, but there's something specific I'm looking for.
Find the constant that we're gonna integrate?
To find that's given actually. Well, it's the element, the big radical with the partial derivatives and all that. Well, that's given. So to set the boundaries, okay. Well, something else before setting the boundaries.
To get the function, you see?
It's given. It's given. Why? Any other ideas? Guys, you have an exam on this tomorrow. Mm-hmm. Mm-hmm. Yes.
Maybe like to find the radius of the circle.
All right, that's one of our end purposes. Yes. So we're getting close. Mm-hmm. Okay, when you set these two equations together, okay, the first equation is in involves three variables, right? When you do the intersection, how many variables are you left with?
2.
How is that useful?
So like set up the double integral, we can find like the balance that way.
All right. Yes, but how? How do we find yes?
You can use the Polar system.
The what?
Polar.
Oh, well, you're getting ahead of the game. I mean, you see it, but you're getting ahead of the game. No, we're not there yet.
You can convert it to just the XY plane.
That's correct, because we want to know the projection onto the XY plane. So do you see how this plane right here works like a knife, cutting this infinite paraboloid? Because we don't know any boundaries about this paraboloid. It's infinite. So this plane is going to cut it. And do you see this? Did you see this intersection which is circular? Boom, slam it onto the XY plane to see the projection. Okay, how are we going to do that? Okay, number one, let me do that. Dash. And I'm going to do another plane. Well, another graph that is going to be the XY plane, okay, which is going to be the projection of the intersection of these two surfaces. So that's what we want to do. And finally, that's to get the limits of integration, all right? And well, so let's do this algebraically first. Again, we're expected to do all this algebraically. Set this guy equal to that guy, that is x squared plus y squared, which is equal to c, which is equal to 9, all right? Hey, we don't need to do any algebra here for real. I mean, what is that? What does that represent? It's a circle of radius 3, right? However, upper hemisphere, semicircle, 9 minus x squared. Lower semicircle, all right? Okay, let's find the partials. Find the partial with respect x, which is 2x. Find the partial with respect y, that's 2y, all right? So let's set up the integral that calculates the surface area here. That is the integral, which is the integral of over the region R. That is ds equal to s. That's the integral of the square root of z with respect x squared plus z with respect y squared plus 1 dA. Alright, do you want to write an integral in rectangular coordinates? I don't think you want to do that, right? Because, okay, let me keep writing the integral without iterating anything. That's the double integral over the region R. That is 4x squared plus 4y, hold on. That is 2x squared plus 2y squared plus 1 dA. That's the double integral over the region R of the square root of 4x squared plus 4y squared plus 1 dA. Think about it. Think about the integral in rectangular coordinates. Do you want to integrate from negative radical to positive radical? Or even even 4 times from 0 to the radical? It's still going to be one single radical. It's not the best choice. Not the best choice. So, what do you think we should do about this integral? Cylindrical, polar. Cylindrical is for a triple integral. Polar is for a double integral. And we're working with a double integral. So, let me rewrite this integral right here. That equals the integral over the region R of the square root of 4 times x squared plus y squared plus 1 dA. What is x squared plus y squared in the world of polar?
R squared.
R squared, alright? So that is the integral 4r squared plus 1. And what is dA in the world of polar? R d theta. Don't forget it's R d theta. Remember that R, we got that R out of the pizza slice, but again we did it more formally with the Jacobian. So that is the Jacobian we need in order to go from the world of rectangular to the world of polar. Alright, limits of integration. How is R varying here? What are the limits for R? 0 to 3. What about the limits for the angle? 0 to 2 pi. Alright. Let's go for it. Okay, so, to evaluate this integral using, with respect to R, this is a great candidate for U-sub, right? Because, the derivative of 4r squared is 1 degree less, and we have that factor, so U 4r squared plus 1 du 8r dr u of 0, u of 3. I'm going to change the limits. If you don't want to do this, that's fine. So 4 times 0 squared plus 1 and 4 times 3 squared plus 1. Okay, so that's going to give us a 1. And that's 3 squared, which is 9 times 4. Isn't that 36? Plus 1 equals 37. Okay? Oh, we need this RDR equals 1/8 du. Alright, so this will be equal to, in the world of polar, the integral from 0 to 2 pi, and the integral from 1 to 37. I'm going to take this 1/8 outside of the integral. That's the square root of u du d theta. And well, that's 1/8 integral from 0 to 2 pi, the integral from 1 to 37 of u to the 1/2 du d theta. Okay? So integrating u to the half, what is that? 1/8, the integral from 0 to 2 pi, that's u to the 3/2 over 3/2 from 1 to 37 d theta. And what else? Okay, so dividing by 3/2 is the same as multiplying by 2/3. 2/3 times a times 1/8, that reduces to 1/12. And let me continue here. So that is 1/12 integral from 0 to 2 pi. That'll be, okay, 37, wait, 37 to the 3 halves minus 1 to the 3 halves d theta. But we need to simplify this quantity. Okay, so this will be, okay, let's see my notes. This is 1/12 integral from 0 to 2 pi. That is the square root of 37 cubed minus 1 d theta. Okay, let me do some side work. Square root of 37 cubed, that's the same as saying 37 squared times itself, 37. The square root of 37 squared, isn't that 37? 37 root of 37 minus 1. Whatever that is, okay? So that is 1/12 integral from 0 to 2 pi 37 root of 37 minus 1 d theta. That's just a constant, right? That's just a constant. 1/12 37 root of 37 minus 1. All right? So in the integral of d theta, what's that? Isn't that theta? From 0 to 2 pi, that equals 1/12 37. Hold on. It's like this, right? 37 root of 37 minus 1. 2 pi minus 0, isn't that just 2 pi? But 2 pi reduces with 12 to give us a pi over 6. 37 root of 37 minus 1. So that's the final answer. All right.